Now our last statement, the third theorem. How do you prove that something is differentiable? This definition, this limit, it's very difficult to work with. So you don't actually usually want to compute with that, but you usually do other things. You use chain rule, etc. But if you wanted to show that something is differentiable, you just show that partials exist and partials are continuous. The limits are usually easier to work with. That's the reason. And okay, this statement is interesting, but the proof is more interesting, I would say. So this is one of the cases where like you almost care more about the proof than the statement. And the picture to have in your mind is a picture of a staircase. We'll soon see how that comes up into play. And I've had attached here just a famous picture of M.C. Escher's staircases. And a completely unrelated note is that there's a very entertaining game, mathematical game, called Monument Valley. It actually has two versions, 1 and 2, which is all about trying to navigate mazes that look like this. For example, something like that, and you have to get this person from here, say, to that point, or some other point. And it all plays it with perspectives, because you can then rotate, say, this bar, and then you can actually go between these two locations. So, oh, you played, yeah, you should definitely, the second one is also very good. The second one is also very good. The first one was, I think, the best, yeah, but the second, yeah. So it's awesome. Yeah, if you haven't played this game, you definitely should play this game. So it's also just very beautiful. It's just beautiful graphics, beautifully designed. Yeah. Oh yes, it can get confusing. Yeah. So, yeah. Okay. But so remember, when you think about this proof, remember the word staircase, because that's the heart of the proof. And there is a staircase lemma, appropriate, or I don't know if I think it's usually called staircase lemma, but anyways, let's call it staircase lemma. And so you have a function from here, and it's an estimate that holds as long as the partials exist. You don't have to be differentiable, just the partials need to exist. So you have a function, you have a point, you have the partial derivatives exist, and for some delta, you have a ball inside the region. Don't worry, I'll draw a picture. And then we're looking at the difference, fx plus h minus fx. I mean, it shows up in the derivative thing, so we want to look at that. And this can be expressed as a sum of partial derivatives times h. Now this is a heads up, this is almost what we want, because what is the gradient? The gradient is partial derivatives. So this is like saying partial 1 of f p1, comma partial 2 f p2, this vector dot h vector. So it's like a dot product. But the thing here that's a little bit annoying is that you have a different point. The pi depend on it. And for convenience, I will just do the two-dimensional argument. I've written the n-dimensional argument in the notes, but understanding the two-dimensional argument is really enough not just for this class, but understanding the proof. So, okay, let's see, before we prove the staircase lemma, let's see how do we use it here. So we want to show that this limit goes to 0. And the difference here is that we have a p there and not x. Okay, so first, we want to use the assumption. So we are proving that if the partials exist and they are continuous, that this limit goes to 0. So let's just first use continuity. So there, for every epsilon, there exists a delta such that if your point is close enough, then the partial derivative at this nearby point will be less than, in absolute value, less than epsilon. Or, the difference between that and partial derivative at x will be less than epsilon over 2. Okay, so let's correcting that. Yeah, of course, it doesn't have to be small, just it needs to be close to that. Okay, so what does staircase lemma tell you? The staircase lemma allows us to write this as something that looks like that, almost. Okay, so if h is less than or equal to delta, then we're within this ball. Okay, technically this delta should be different from that delta, but yeah. But let's just allow it for now, this slight ambiguity. So fx plus h minus fx, that can be written as, by the staircase lemma, as partial I of f pi times hi. But now you have two sums that look the same, except that the factors are different. So you merge the terms, you merge them together. And what you get here is, maybe I'll add one step to this since we have a good time. So what is this? This is sum from I equals 1 to 2, absolute value, make it less than or equal to, well, the absolute value is already inside. So fi pi minus partial I f x. So the difference between these terms times the absolute value of ai. And then from there, that's the numerator. It's bound by that. Now, absolute value of ai is bounded by h. I mean, you could think that you have h divided by h. So the component is always less than the length of the vector. So you cancel those out, and what you're left with is the sum of the differences here. But what is the sum of the differences? It's epsilon over 2, epsilon over 2, epsilon. So the error here comes from the difference between the points, but their continuity tells you that doesn't matter. Okay. Now the proof of staircase lemma. This is the tool that, like, if you're, I think is one of the nicest ones here. So proof of staircase. And so what is the picture that we have? We have x here, we have y there, and we are summing up h. Again, kind of this, we have these three variables, x, y, the difference, which is h. And the difference between the function values, how we will represent it is by going along a staircase. So first we change the x component, and then we change the y component. Okay, this doesn't really maybe look like a staircase, but if you imagine the three-dimensional picture of this in 3D, so like in that game, you'd have 2 points, x and y, and you'd have 3 steps. You'd change the x coordinate first, then you would change the y coordinate, and then you change the z coordinate. Let's move that point. So then it starts looking like this multi-dimensional staircase. I mean, what that game is all about is playing around with those staircases that go in all 3 dimensions. Once you get to 4 dimensions, you lose intuition. There's kind of a 4th direction that you go to, a 5th direction that you go to, a 6th direction. I mean, these are kind of all keep on going. But each of them, yeah, how you organize it in your mind is you do it in 2 dimensions and you get notation that what works, and then you go from there. So how do you organize this? You have the first point here in the ladder, that's just x, and then you change the first component, but that you can do by adding h1e1, and then you take that point and you add the change in the other component, so h2e2. I mean, in general, it would be xn plus 1 is equal to xn plus xn plus hn en. Or, well, the indexes here are a little different, but in the notes you'll get it right. So we write a sequence of points like this that form a multi-dimensional staircase that connects the 2 points. But the benefit of this is that the difference in the function value, you can write as a telescoping sum. So this time you only have 2 terms. So it's the difference when you only change the y component and difference when you only change the x component. But now you get a nice thing. When you're only changing the y component, you are a one-dimensional function. When you only change the x component, you are a one-dimensional function. So you write these as one-dimensional functions. So let's look at the first difference here. This is a one-dimensional function, x0 plus TEI. So when t, this one-dimensional variable, is h1, that's x1. When t is equal to 0, you are fx0. So the difference here is the same thing as the difference here, g1h1 minus g1, 0. Partial derivatives exist, so this thing is differentiable as a single variable real function. You go back to your 131A textbook and remember that you have mean value theorem. Well, mean value theorem for this function tells you that there's a point between a 0 and h1 so that this difference is equal to the derivative times h1. But that derivative is the partial derivative because you're only moving in the x direction. So it's the first partial times h1. And you do the same thing for the other term. This time you get a term s2, which is between 0 and h2. And yeah. But okay, these are the points that you want. So P2 is x1 plus s2 e1. P1 is x0 plus s1 e1. And the nice thing is, what is the distance between these points? The difference between P2 and x is, well, it has the difference in the h1 x component plus the difference in the y component. But this y component is at most h2, so this whole thing is less than the norm of h, which is less than delta. And the same thing here, that's less than delta. In the picture, this is obvious. If you have 2 points inside the y is within distance delta, this ladder will only put the points closer. In 3 dimensions, the same picture holds. So, but the algebraic calculation would look something like this. But okay, what we get with these points, we expressed it as a sum of these 2 terms, this term and this term. And we set those points as that, so we just rewrite it as this, and we're using the sum notation, and we're done. So we're good. This proof is done.